This is the second video on the rate of reaction in chemical kinetics. So during the first video, I explained what rate of reaction actually means and ways to measure them. So right now I'm going to start with the collision theory. So the collision theory basically states what is necessary for reactants to become products within a reaction. So as I explained before, every reaction has reactants that will become products, and the rate of reaction basically explains how fast this happens. So the collision theory explains why and under what conditions do reactants become products. So the collision theory states that reactants will interact to form products only if they have sufficient force and the correct orientation. So this means that there are two important things that must happen in order for reactants to turn into products. First, they must have sufficient force, and second, they must have the correct orientation. So right here I have an image of two reactants that could be A or B moving around in a container, and we can see that they collide. But even when they collide and they grasp together, they must follow these two conditions, which are they have sufficient force and the correct orientation. So what the collision theory also states is that the higher the kinetic energy of a substance, the more the particles move. And kinetic energy is generated in multiple ways, but one of them is temperature. So the more kinetic energy they have, the more the particles move around like crazy, and the more collisions happen between them. So if you're running around in a room, you have more chance of bumping into someone else than if you're just walking around in a room and you're actually paying attention to what you're doing. So successful collisions, this is of extreme importance. The main idea of the entire kinetics unit is more collisions equals more probability of success. So if you bump into a lot of people, there is a higher probability that that collision is going to work when considering turning into products. So the two conditions were, once again, that they must have the correct inclination or orientation, and that they have sufficient kinetic energy. So to this side, we can see the idea of inclination or orientation. We can see that they have to be in a specific position in order to successfully collide, and this position is seen right here. You will never be asked to actually draw it out. You just need to know that there must be a correct inclination or orientation for a successful collision to take place. But the most important part is that there must be sufficient kinetic energy, and the more things collide, the more probability that they collide well and that they create products. So this is an important concept. It's the energy for collision. So before I explained the correct inclination or orientation, and now the idea of energy. So the energy required for a successful collision is called the activation energy. So what the activation energy does, it overcomes repulsion between molecules and breaks sufficient bonds. So for two reactants to turn into a product, there must be sufficient energy, and that sufficient energy is called the activation energy. So when we drew these graphs in chapter 5, exothermic and endothermic graphs, there was also always this little bump. And what this little bump means, this is the EA, or the activation energy. And this is the energy required for the reaction to take place. So this is the idea of sufficient energy. So just to sum up, the collision theory states that reactants will only form products if they have sufficient force or energy and they have the correct orientation. So ways to make the rate of reaction faster or slower. There are different methods that can increase or decrease the rate of reaction. You must be familiar with these, and you must be able to explain them. So the first way is temperature. So higher temperature leads to more kinetic energy. And as we stated before in the collision theory, more kinetic energy means more movement of particles. And more movement of particles means more collision. So as you can see in this diagram, these little red lines represent the energy or how fast they're moving. And you can see that they're moving really slow. However, once they're moving really, really fast, you can see that they'll collide a lot more. And once again, more collisions equals more successful collisions, which means that reactants actually turn into the products. So the higher temperature, the higher the rate of reaction. So if this is 10 degrees Celsius, for example, and this is 20 degrees Celsius, this one will have a higher rate of reaction because the products can move around, the reactants move around a lot faster and collide with more energy and therefore can create products. The second way is concentration. So higher concentration means more full. So for example, if I have a flask with HCl and NaCl, and I increase the concentration of HCl, I am making the flask more full of HCl. A more full flask means more chance of colliding with others, which once again, more chance of colliding equals more successful collisions, and then a higher concentration therefore means a higher rate of reaction. So what I put in here is an image, and just so you understand, if I have a room with one other person, it's me and one other person in a room, it's going to be very unlikely that if we move around we actually collide, correct? However, if I have a room with 30 other people and it's a small room, then the chances that if I move around I'm going to collide with someone is a lot greater. So by increasing the population of the room, or the concentration of people in the room, I am increasing the chances that I collide with someone else, and therefore increasing the rate of the reaction. So more concentration equals higher rate of reaction. This one, the particle size is a little bit harder to grasp. Basically, the larger the particle, the less surface area there is. So in this example, we can see that there is a square, a marble chip, which is what the image calls it, and that there are the other reactant is moving around it. It is you can see that the only places that the other reactants can collide is along the surface of this square. However, if I decrease and cut this square in half, the places in which I can collide will actually increase by a lot, which means that the smaller the particle size, the more chances there are, or more space there is to collide. And then once again, more collisions equals more successful collisions, which equals higher rate of reaction. So right here I have a larger particle equals less surface area. So this entire square has less surface area than if I had each tiny square where I have 1, 2, 3, 4, 1, 2, 3, 4 sides, 1, 2, 3, 4 sides. So a larger particle has less surface area. Less surface area equals less chances to collide. Less collisions equals less successful collisions. So a larger particle equals slower rate of reaction. What most things will do is flip them around, and it'll say, if you grind or if you powder a substance, will the rate of reaction increase or decrease? If you powder a substance, it means that you're increasing the surface area, which means that the rate of reaction will increase. Large particle, slow rate. Small particle, fast rate. The next is pressure. So we know that if you increase pressure, you will decrease volume. So right here you have a pressure. If I increase that pressure, the volume is actually a lot smaller. And smaller volume equals more compact and consequently more collisions. So the chances that these will hit each other is a lot smaller than the chances that these will hit each other. So the idea is more pressure equals less volume, which equals less space, which equals more collisions and more successful collisions. So more pressure equals higher rate of reaction. And finally, we have the addition of a catalyst. So what is a catalyst? A catalyst is a substance that decreases the activation energy required. So I explained what activation energy was in this, which is the energy required for a successful collision. And a catalyst decreases that energy. So instead of having a big lump like this one, I would probably have a lump that's half as big, which means that I require less energy to be successful. So the addition of a catalyst will increase the rate of reaction. But since this is a little bit hard to grasp, I created an analogy, which is that a teacher is giving an exam, and the pass grade, which means that the grade you need to get to pass, is a 90, and only 2 students are passing. Then what the teacher decides to do is decrease the passing rate so that now it's a 70. Now more students are able to pass. What the catalyst does is that it decreases the expected energy required, and then more molecules can actually collide with sufficient energy. So instead of needing an A to pass, you need a C to pass, which is a lot easier. So what a catalyst does is it decreases the energy required for you to pass or for you to have a successful collision. So the last topic within this unit is Maxwell-Boltzmann distribution curves. These are basically Maxwell-Boltzmann distribution curves is this graph. It basically states the amount of kinetic energy and the number of molecules. So you can see that in the beginning, there are, if this was, for example, 1, 2, 3, 4, 5, 6, 7 on a scale, you can see that the ones with low kinetic energy, there are a lot of molecules. And with really high kinetic energy, there are little molecules. So basically, the Maxwell-Boltzmann distribution curve states that there are a lot of molecules that have little kinetic energy and less molecules that have higher kinetic energy. And there, you must be able to draw this, but you also must be able to apply it to 2 different scenarios. The first of them is temperature. So we can see in red that there's a Maxwell distribution curve, just like the one we saw in the previous slide. And this is for 300 degrees Kelvin. And you can see this line here expresses the activation energy. This green line right here is the activation energy. So this is right over here, under the red line, is the number of molecules that have sufficient energy to collide successfully. And then when you increase the degrees by 10, you can see that the curve will shift towards the right, and that you will actually add all of this area and all of these molecules. So by shifting and adding temperature, more molecules can successfully collide. So you must understand for this graph is that the area under the red line is smaller than the area under the blue line, and that this area is the number of molecules that can collide successfully because they have sufficient kinetic energy. So what the temperature does, it shifts the graph a little to the right, and it increases the area and the number of molecules that can collide with sufficient energy. And the second curve that you must know is the catalyst curve. So as I said before, this is the activation energy for a reaction. So this here is a number of molecules that have sufficient energy to collide. And when you add in a catalyst, as I explained here, you are lowering the bar, which means that you require less energy to collide successfully. So this is the line that you must be able to draw in a catalyst curve. It just means that now, when before you needed like a higher level of energy for a successful collision, now you need less than that. You need just this, almost half. So you must be able to draw this and explain that this blue line is because of a catalyst that decreases the kinetic energy required for a successful collision. So while before only these molecules could successfully collide, now all of these molecules can successfully collide. So that's basically the idea for kinetics. You must be able to explain what is rate of reaction. You must know the ways that you can measure the rate of reaction. You must understand and be able to state the collision theory. You must know, and this, most importantly, is the best part because it falls on every exam. You must be able to explain the ways to change the rate of reaction. So temperature, concentration, particle size, pressure, addition of a catalyst, and you must be able to draw these 2 curves. Temperature, higher temperature will shift the graph to the right, and there will be more area under the graph that can collide with successful energy. And a catalyst lowers the bar so that more people can actually pass the exam or collide successfully. So that's rate of reaction.